Hey physics friends, Mr. Collier here, and today we're going to talk about circles one last time, addressing the real question, why do objects move in circles in the first place? And the answer is going to end up being centripetal force. So just as translational motion can change, and so you can have an object that accelerates, we can also have an object that accelerates when it's moving in a circle. We call this angular acceleration, and we use the little alpha. So what it's going to be is a change in velocity over time, just like it is when we talk about translational acceleration, only now we're going to talk about angular velocity changing over time. And so there are two ways that we can write that. We can talk about subtracting the speeds or just use the little delta to talk about a change in speed. And the units for this are going to be radians per second squared most commonly, but you could also convert it into revolutions per second squared as well. Here's a simple sample problem about this. Say we have a CD that accelerates from rest to an operational speed of 500 RPMs in 3.5 seconds, and we want to find out the average angular acceleration. To do this, we need to know how fast it's going at the beginning and how fast it's going at the end. At the beginning, of course, it's not moving, and then it will accelerate to 500 RPMs. We just need to convert that, though, to radians per second. So since it's per minute, we'll divide by 60 to make it per second, and then we'll multiply by 2 pi, which is how many radians there are in a revolution. And that leaves us with two different speeds, 0 and 52.4 radians per second. Final minus initial, and then we'll divide it by the time that it takes to do that acceleration, and we will have an acceleration of 15 radians per second squared. We can then figure out the acceleration if it comes to a stop. We can basically do the opposite, so final minus initial. Now the final is 0 and the initial is the speed we calculated, and divide it by the new time, and we'll have a negative instead of a positive, which indicates an opposite direction. One thing we could also ask is, what is the acceleration while the CD is being played? And the answer to that would be 0, since at that point it is spinning at 500 RPMs consistently, so no acceleration. Another thing we can talk about when looking at rotational motion is rotational kinematics. So instead of using the kinematic equations that we've learned before, we can just swap out some of those variables for their circular counterparts. So instead of regular old v for velocity, we've got our omegas, and we've got thetas instead of displacement, and alphas instead of acceleration. But other than that, they are these same equations just subbed out, and we can use those to solve some kinematic circular problems. Now, if an object is moving uniformly in a circle, we know that its angular position is changing, but it has a constant angular velocity and therefore a constant tangential speed. But if something's moving non-uniformly in a circle, like it's spinning up faster or slowing down, then its angular position, of course, is still changing, but now its angular velocity is also changing, and so its tangential speed is also changing. And if that tangential speed is changing, it must be accelerating. So let's talk a little bit about that. So a tangential acceleration will be happening in the same direction of the changing tangential velocity, and we can calculate it with the equation acceleration tangential is equal to the radius times the angular acceleration. And something interesting to think about here is that if an object is accelerating in a circle, there must be one force that's changing its direction, keeping it in that circular path. But there also must be another thing causing it to spin faster, and that is sort of a tangential force. And so the net force acting on it could be a kind of an angle when you kind of add those two together, and if it's speeding up, it'll be in one direction, and slowing down would be in another direction. So we'll draw some free body diagrams during our problems in class of this. And here's a couple more diagrams kind of illustrating this concept that if something is moving uniformly in a circle, there must be some sort of acceleration that causes it to change direction to move in that circle, as circles are constantly changing direction. But if it's moving non-uniform circularly, there must also be something that is speeding it up or slowing it down in that circular path, so an additional acceleration, an additional force. And this brings us to why objects move in circles in the first place. This is something called centripetal acceleration, and it's the acceleration needed for any circular motion to happen. I think the most easy way to think about it is that if an object is moving with some velocity, and then it changes directions and changes directions and changes directions. That's what a circle is. It's something that's constantly changing direction. And we learned that velocity is speed plus direction. So therefore, if something's changing its direction, it must be accelerating. And we can look at the direction of this acceleration if we think of an object moving in this direction at one point in time, and then same circle, now it's moving in this direction, and then we do a little bit of vector addition, and we find that the resultant change in velocity is the difference between those two vectors, and it is pointing in toward the middle of a circle. Another way to think about it is, how do I get a thing that's moving straight to curve? Well, I'm going to need to apply a force in a direction that makes it curve, and if you look at the sum of those forces, they are always pointing toward the center of the circular path. And if an object is accelerating, we've learned that there must be a force acting on it, and that force is called the centripetal force. It's the force that causes an object to change direction that makes it move in a circle. It is a force toward the center of the circle. Not to be confused with what people call centrifugal force. People think of the tendency of an object to fly to the outside of a circle as a separate force, but in reality that's just the inertia of the object, its tendency to try to move in a straight line. Centripetal force is what keeps it moving in a circle, and that is a real force that we can measure. It's equal to mass times centripetal acceleration, which we showed you how to calculate earlier, and centripetal acceleration is equal to v squared over r, so we relate it to the tangential velocity and the radius of the circle. We can also rewrite that as the radius times the angular velocity squared, and we can also then put these things together to have the centripetal force equal mass times velocity squared over r. So a variety of different equations that will let you calculate forces and accelerations of objects moving in circles. And that is it for this section, so good luck. See me if you have any questions.